Thank you, Bruce, for the nice introduction. Like Bruce said, I just finished my PhD in physics with concentration in optical physics. And my topic was laser-induced fluorescence spectroscopy for application in chemical sensing and then optical refrigeration. The chemical sensing is what is the laser-induced breakdown spectroscopy for detection of chemicals. And then the optical refrigeration also I'm going to talk about. We develop our own crystal using rare earth ions and then dope it with a certain host materials. These materials are at a certain transitional level. They have a very broad band. And then above a certain mean wavelength, these materials are expected to cool down to a very low temperature, which has numerous applications, especially for space. And then sometimes to some of the papers have even reported that it's possible to use it in for biomedical applications. Well, like I said, my outline is divided into two. The first one is for the chemical sensing. I'll talk about introduction and then the background of the laser-induced breaking down spectroscopy. And then after that, I'll move on to the experimental techniques that I use. I'll show you the setup and then show you the process involved. And then from there, I'll show you some of the interesting results that we had. And these results has been published in SPICE, one of the SPICE papers or so, and one in optics also. And then from there, I'll move on to the optical refrigeration part. I'll talk about introduction to the optical refrigeration and also talk about some of the background, talk about material preparation, show you the experimental setups, and then the results, and then draw a conclusion to the part two also. Well, the first part, which is the LIBS. So let's move on to laser-induced breakdown spectroscopy, called LIBS. Introduction, LIBS have been in existence for over 50 years now. Most of the work that has been done so far concentrate on the UV visible wavelength region. It's used for detection of elemental composition from either a solid, liquid, or gas. And it has the capability of detecting and identify chemicals, biological, and explosive material. And the main component of LIBS is you need a very high power, short pulse, tightly focused laser beam. And this is experimental setup for conventional UV visible LIBS. You have a very high power laser. You focus it into your target. It ambulates a very small amount of it. It forms a plasma right over there. But as the plasma expands into the ambient air, it decays. The plasma emits light. And as it emits light, the light contains information of the atomic and molecular emission signatures of the target material. So the light is then collected by a fiber optics or CCD camera, which is connected to a spectrometer. The spectrometer resolves the atomic and molecular peaks into their respective wavelength peak. And this is an example that you see here is emission spectra from sodium chloride crystal. And this tells us the atomic peak with respect to neutral sodium atom from that material. In this case, within this wavelength region, it is very difficult to detect the anions attached to the sodium compound. What are some of the advantages? That is why this technique is very more useful, because there's already existing techniques for detecting of atomic and molecular emissions. Some of the advantages are it's applicable to all forms of material, like I said before, being it liquid or solid or gas. And little or no sample preparation is required. You can shine the laser beam, and if you have the right equipment, You can collect emissions, and then it's going to tell you exactly what that specific target material is made up of. And because of the small size of, and let me point out this, because if you look at some of the conventional techniques available, which have been in existence for a very long time, you have to do a lot of what? Sample preparation, and it's time consuming also to do that. And because of the small size of the focal beam, this gives you a precise measurement. Henceforth, it has a very high spatial resolution. And this technique is currently being used for standoff detection of the threat, which is you can put your instrument right over here and it can measure as far as about 50 feet away. It's going to tell you exactly the elemental composition of that specific target material. And here are currently some of the applications that is being used in the mass to detect the elemental composition in the mass. And it can also be used as a fingerprint from any residues. And currently it's being used by a lot of law enforcement across the country for forensic analysis. And then military, some of our guys on the warfare are using what we call LIBS backpad to detect explosive material also. And this is a typical example of the standoff detection techniques being used in the LIBS. Well, let's talk about some of the processes involved before you get the plasma. The first one is that you need the laser beam goes straight to the target surface. The target material absorbs the laser energy. And then when the laser energy on the target surface exceeds the threshold amount of that specific material, it ambulates a very small amount of it. After that, subsequent trace of the laser pulse that goes and hit the ambulated mass actually interact with it, and then they produce a plasma. Initially, the plasma plume is dominated with what we call the continuum emission and the brainstorm. And then the continuum emission within the plasma overshadows the atomic and then molecular emission within the plasma plume. And these continuum emissions have a very short lived time. So as the plasma plume expands into the ambient air and cools down, this continuum emission decays out, and then the atomic and molecular emission within the plasma becomes clear to be detected, as we see here. But what we have been able to observe right now is that the atomic emissions have a very sharp peak, while the molecular emissions have a very broad band, as we'll see later on. Well, due to the nature of the plasma plume, we use what we call time-resolved techniques to detect these emission spectra, emission signatures from any target material. Because, like I said, the plasma plume is made up of what? Different species. The first part is the continuum emissions, followed by the ionic emissions, and then atomic fingerprint, and then molecular emissions. And they all occur at the different time scales. So you need something to get out, or a specific window to detect your emission signatures. So what happens is that we use what we call a gate delay and then the gate width. The gate width is actually the time window within which the emission studies are being carried out. So the purpose of the time delay, time resolve techniques is to gate out the black body, because that totally overshadows the specific atomic and molecular emissions within the plasma plume. So this is an example of emission signal as a function of time for neutral sodium atom occurring at around 1.2 micron region. This is a transient that we see over here. As you see over here, realize that the continuum emission initially produces a very sharp peak, and then it decays out. And then it forms another bump over there. Beyond that, where it stops and starts forming another bump, that is where atomic and molecular emissions actually occur. Henceforth, you have to set your gate beyond that point to detect the atomic and molecular emissions within the plasma plume. Well, like I said before, this technique has been in existence for over 50 years. So one will ask me, why are you then doing it again? Like I said, most of the work that have been done so far concentrate only from UV to the near infrared region. And even the early part of the infrared region, normally we call it quiet infrared region, because they don't give us any signature on molecular structures. And because of that, it is very difficult to actually, I cannot use only atomic signatures to characterize materials very well, because it depends on your surrounding, the environment in which the plasma plume is formed. If you produce a plasma plume under air, there is influence of oxygen, nitrogen, that can also affect your emission signature that you're going to get from the plasma plume. Henceforth, what we thought is that it would be better if we can extend this study to the longer wavelength region from 1 micron to 12 micron region, because this region, we know that molecular signatures occur in this infrared region due to the rotational and vibrational transitions occurred in this region. Henceforth, because we believe that also this is going to add additional information to the existing UV visible LIBS, and it's going to make identification of any target material very easy and simple. So we took commercially available sample, that is alkali halides, potassium chloride, sodium chloride, and then the chloride salt, nitrite salt, and then perchloride salt. And then we, after that, after measuring these chloride salt, we also tested this technique on a black powder from ESTES rocket engine. And then we were able to identify the emission signal or the chemical composition of the rocket engine, as we're going to see later on. One will ask you, how do you identify, how do you know that this peak is actually for potassium or sodium? What we did is that there's a database available from NIST, which gives us atomic signatures. And then there is also an infrared emission spectra available, where you compare your data with that of the NIST database for both atomic and molecular emission signatures, as we're going to see later on. So let me show you my experimental setup, some of the equipment that I use. Well, like this is the example of how the commercially available crystal, we press them initially into a tablet, and then after that, we mount it on a translation stage right over here. The translation stage is controlled by a step motor controller, so we scan within a certain wavelength range. The laser we use, neodymium yak laser. The beam is directed onto the sample mounted on the translation stage. And then it produces the plasma. It expands, and then we collect the lens by using the two collection lenses that we have over there. And then we put a long pass filter to filter out any backscatter radiations. So the spectrometer collects the emitted light and then resolve them into their respective emission peaks. We use two different detectors, indium actinium from 1 micron to 5 micron, and then from 5 micron we use MCT detector. The detector collects the emissions and then converts it to electrical signal, which we monitor this signal in our oscilloscope. And then the broadcast average, because we are getting a laser pulse, averages the signal and then store them in a computer. We use, like I said, different pass filter. Energy per pulse on most of the sample will range between 50 to 75 millijoules. And this is the actual experimental setup. This is the translation stage that we use. This is the spectrometer. This is one of my detectors. Then these are the collection lens. This is the one that we have here is the commercially available fiber optic instrument that's measured from 0.35 micron to 1 micron region, which is available on the market. And that one gives you just a single shot. It's going to tell you specific information, that is atomic information of your target material. And this is the locking and bus card averager that I use, and then this is the step motor controller. The laptop that you see here controls the spectrometer, and then this is the 1064 Nedenium IR laser, and we still have 532 Nedenium IR laser also. Well, let me show you some of the results that I had for the near and then mid infrared region, which is going from 1 micron to 4.5 micron region. I use a time delay of 15 microseconds and a gate width of 16 microseconds. And in that case, I started with the potassium containing compounds, which is the potassium chloride, potassium nitride, and potassium chlorate. I started with the potassium chloride, which is not a very complex compound. And in that case, I observed 3 strong emission peaks for the near infrared region, extended into the mid infrared region, and observed additional 4 peaks. I repeated the same, using the same set of parameters, and again, same set of parameters. I did it for potassium chlorate and sodium nitride. And then I observed the same emission peaks that I observed in potassium chloride. I said, okay, let me find out if air has any influence on these emission spectra. So using the same set of parameters, I repeated the experiment for air, and I observed that air has no influence on this peak. But looking at this data, it is very difficult to distinguish between which compound is which. So based on that, I compared these emission peaks with the NIST database, and I found out that each of these peaks correspond to neutral sodium atom. And based on from the NIST data, you can really know there's a sign transition, that specific transition at which each of these peaks or signatures occurs. And that is what we see over there. And then I also did the same thing by using sodium containing compound with the same anion. And then for the sodium, I observed just 1 strong peak for all the compounds in the near infrared region. I extended it to the mid infrared region, the same thing. Like I said before, it is very difficult to distinguish between which one is which. And if you have such a mixture of compounds around you, how do you identify it? It tells you that if you work within this range back to the UV range, it is very difficult to distinguish between some of these compounds. And if you observe it, what we observe also here, all the peaks belong to neutral sodium atom. And none of the anions attached to the sodium or potassium were identified in this region. Henceforth, we decided to extend it to 5 micron to 12 micron region. In this case, we used the microcardyon telluride detector, which is called the MCT. And we set our time delay to 30 microseconds. Because, like I said, we're trying to detect both atomic and molecular emission. And based on the plasma Plume diagram that I showed you before, along the line, 2 of them can overlap. Both atomic and molecular emissions overlap. So we try with a different gauge delay or time delay, and then we found out that 30 microseconds will be the best place to detect both atomic and molecular emissions. So based on that, using the same set of compounds, that was used for the previous one, which is the near and mid-infrared region. We scanned potassium chloride from 4.4 micron to almost 12 micron region. And then we observe only some few strong peaks over here. Based on this one, chlorine was not identified. Remember, chlorine does not produce, potassium chloride does not produce any vibrational transition within this range unless you go to the far infrared region. That is why it's being used as a lens, focusing lens in most of our optics stuff. So we decided to do it, repeat, using the same set of parameters. We did it for potassium perchloride. And then that one, we observed one broadband right here, which overlaps with one of the peaks from the potassium chloride. And then repeated it with the potassium chloride. And that one, we observed additional broadband over here. And then we did this for potassium nitride. And then we observed that initially from about 6.5 region, you see a very broadband peak, and then overlaps with this peak that we observe right over here. So based on that, we decided that let's compare this data from potassium chloride with the NIST database. And then we observed that only one of the peaks correlated with the NIST database, the one at 6.25 region. And then to make sure that this broadband that we see here is a molecular signature, we took an FTI absorption spectra and then compared it with our measurement. And behold, we saw a very strong correlation with the broadband emissions over here, over there, and then over here. And this broadband for the potassium perchloride represent the chloride molecules. And the broadband that we see there is due to asymmetric stretch vibrational mode that occurred in that region, similar to the perchloride and then the nitride. To make sure these broadband that we seen over here is the real thing, we repeated it with the sodium-containing compound also. And then similarly, we observed this broadband within the same region as we found over here. And then for the potassium chloride, almost all of the peaks that you see there were correlated with the NIST database. And if you look at our air, initially we saw initial broadband from 4.4 micron region to about 6 micron region. And that is due to the nitrite vibration due to contribution of nitrogen and oxygen in air. And this occurs in all the emission spectra that we had. Well, based on these results, we decided, why don't we take an unknown sample and test it and see the efficacy of these techniques. So based on that, we took a black powder from ESTES rocket engine, which we know that a black powder is made up of charcoal, and charcoal is a carbon. And then it's made up of potassium nitride, and then sulfate. So in these ratios. So in that one, what we did was that we pressed this one also into a tablet, mounted using the same set of experimental parameters, which is 30 microsecond delay and a gateway of 15. And that one, we scanned from 4 micron region to 12 micron region. Like I said, near and early part of the mid-infrared region is what we call quiet infrared region. So they don't really give us any molecular signature. So we were not interested in that region. Henceforth, we observe initial one strong peak around 6.25, and that corresponds to potassium, neutral potassium atom, which was identified from here. And that is the only peak that correlated with the NIST database. And then we also compared it with the nitrite. And then we observed that there's a strong correlation with our measurement. Sorry. Thank you. With our measurement, as you see over here. And then compare it with the sulfate. And then we saw a very strong correlation within these measurements and that of the FTI absorption spectra. Well, in conclusion of the part 1, based on this experiment, we were able to actually identify intense atomic spectral line in the near and then mid-infrared, and then the longer wave ranging from potassium-containing compounds. And this atomic spectral line show a strong correlation with the NIST atomic data base. And in addition, this is the first evidence of molecular LIBS emission structures. It has never been done anywhere. That was the first time we had such results for the molecular emission signatures. I also did, because in every technique, you have to know the efficacy. What is the lowest possible limit that can be detected? So we did a limit of detection on the perchlorate anion in the potassium chloride, and we found out that the limit of detection was around 14.7 plus or minus 0.5 weight%. And we know that this value is very small. And then we are currently working on that to improve on our techniques of detecting systems and then the matrices effect. So, but due to time, I cannot go into the detection limit. It's at the back of my slide. So when I finish, if you're interested, we can go into that one also. So let's move on to the second part, which is the optical refrigeration. Well, optical refrigeration actually deals with where an energy is actually removed from a solid by using a principle called anti-Stokes fluorescence. And this is an optical refrigeration of two-level system. This is the ground state, and then this is a side-test state. What we do is that before you do anything with respect to optical refrigeration, you have to know what we call the mean fluorescence. So you tune your laser beam slightly above the mean fluorescence. If you tune it below the mean fluorescence, you're going to heat up the crystal. But if you tune it slightly above the mean fluorescence, you expect the crystal to cool down. So what we do, you tune your laser pump slightly above the mean fluorescence. The electrons or ions in the E2 level get excited and then move straight into the excited state. When they get to the excited state, they go through certain transition called non-radiative realization. And then they go through non-radiative realization, that is from E3 to E4, until it reaches what we call quasi-equilibrium. What happens in the quasi-equilibrium is that it absorbs the energy due to the vibration of the host material, because we have a dopant and then we have a host. But then the host material causes vibration within the excited state and then the ground state. It absorbs that energy and then bring it down to equilibrium. After that, it emits light. The light that emits has the energy that is equivalent to, have a wavelength that is equivalent to the mean fluorescent wavelength. But what we know is that the energy difference between the mean fluorescence wavelength and then that of the pump is what is removed from the material, and then it cools down the material through anti-Stokes fluorescence. This material is expected to have a very high quantum efficiency and also have a low background absorption also. And this is a conceptual design of the optical refrigeration system. You have a laser diode here. You focus it into the crystal, which is here, and then you have a very high reflectivity mirror, one here, one here. it goes back multiple paths to cool down the material. And then there is a timer link that conducts the cooling of the material to the infrared detector to cool down that infrared detector. Well, let's go to cooling. Optical refrigeration is characterized by a quantity called cooling efficiency, which is defined as the cooling power divided by the absorbed power. And the cooling power divided by the absorbed power will give you this. But like I said, there are two quantities that have to be taken into consideration. The first one is the quantum efficiency. The quantum efficiency actually depends on the radiative decay and then non-radiative decay. And that one is due to the contribution of the non-radiative decay. If the non-radiative decay is large enough, it's going to affect your quantum efficiency, reduce it, hence for your cooling efficiency is going to go down. Similarly, the absorption efficiency also that you see here depends on the absorption coefficients plus and then the background absorption coefficient. The absorption coefficient depends on temperature and wavelength, while the background absorption is assumed to be temperature independent and wavelength independent. And the cooling power is defined as this. This is the mean fluorescence energy, and then this is the pump wave energy. And when we change it, convert it into wavelength, this is where we arrive at. That is why we have it here. And the mean fluorescence wavelength that you see over here is also defined as this. Well, in case if we have an ideal material, then we expect to have what? Ideal cooling, which in science or in physics, I know there is no situation that is an ideal. We never get an ideal case. But in case if we had an ideal case where there is no background absorption in our material, no non-radiative decay, then we expect that cooling efficiency will increase with the increase in what? Pump wavelength. But as we go on, we will see that that's not the case. Well, let me just give you an introduction to some basic rare earth ions. Basically, currently, this is what have been worked on by a group in New Mexico, and they have been able to reach a temperature of about 93 Kelvin, below room temperature. And this is the material, the thulium that I work on, which have an electronic configuration of this. But what we know is that it consists of 4F orbital over here. And this is the electronic distribution of the rare earth ion. We have 4F electron here. The 4F electron is responsible for the optical transition property of the rare earth ion. And this is shielded by the, partially shielded by the X, 5X and 5P and 6P electron orbital. Hence, for when doped with any crystal, it causes a small host induced splitting at both the ground state and then the excited state. This is the energy diagram for the thulium rare earth ion. And this is our sign transition that we have. But this is a specific transition that actually work on, and that is a 2-micron region. Well, let me talk about the material preparation. Well, these are commercially available material, which is the lead chloride and potassium chloride, and lead bromine and potassium chloride. This material was synthesized and then transferred into what we call a horizontal zone refinement for purification. And this is the experimental setup for a horizontal zone refinement. This consists of a horizontal tube. The crystal or the potassium lead chloride and potassium lead bromide is put in a different amp. And this amp is then inserted into this horizontal tube. Within it, we have what we call, within it, we have a step motor controller connection within it that controls the movement of the amp during the purification of the material. And it runs translation speed of about 10 millimeters per hour. So it takes about a month to develop one just host material. So after the purification, we obtain this example of undoped KPC. We observe an impurities right here, which is kind of black. So we use the clean pad for further crystal growth and then dope it with the rare earth ion. The reason why we use this material is that it has a very low phenol energy. Henceforth, we expect that the non-radiative decay contribution from this material is going to be very small. Henceforth, our quantum efficiency is going to be very high for the cooling. Furthermore, we took 1% of thulium doped crystal chloride and then bromine powder, and then dope it with corresponding undoped KPC and then KPB. And then we did further purification because these two compounds also contain some impurities to remove or reduce the oxygen-related impurities in it. And we use a technique called vertical Bridgman growth techniques, which consists of two temperature control. One is right here, one is right here. And this ensures that the crystals are met and then mixed very well. And then this also is carried out for about 2 months for just the crystal growth. And then finally, this is the piece that we had for the thulium KPC. And then this is the piece that we had for the thulium KPB. And a piece of each were cut and then polished first for, we have to do spectroscopy analysis. And then before then we move on to the laser cooling part. So the experimental setup, we started with a temperature dependent study on the fluorescence spectra. So what we did was that we polished small piece of each crystal. Hey, let me say this before I go on. We included another crystal, which is also commercially available. That was not developed by us. That is thulium yak. To include it purposely for comparison with our measurement. So as we go on, I'll include that result. I'll talk about it just a tiny bit. So we mounted about 1 millimeter thick of each of these crystals on a cold finger, which is connected to cryostat. And then we use 1795 diode laser as our excitation source, and then directed it into the crystal, collect the emission by using 0.3 meters infrared spectrometer, and then we use indium antimonide, and then monitor the emissions right over here, and then Lockyer profile process the data, and then store it on a computer. We measured from 10 micron to 10 Kelvin to 300 Kelvin for each crystal. And then we did the same thing for the absorption studies also. What we did was that we measured the baseline transmission without any crystal, and then placed down the crystal right over here, and then measured the transmission between transmission through the crystal by using the infrared spectrometer and then indium antimonide. After that, then we use the Lambier's law to calculate for absorption coefficients. So this shows the spectroscopy result, temperature dependence fluorescence spectroscopy. This is thulium KPB. What we observe in these two crystals was that as the temperature decreases, the intensity of the fluorescence spectra increases. As you see here, this is 77 Kelvin, which is right here. This is 150, and then this is 300 Kelvin. But in the case of the LWIR, we observe that as the temperature increases, the fluorescence intensity increases. This is due to the fact that there is more thermal population at the 4F excited state than that of the thulium KBC and KPB. So what we did was that we did then determine mean fluorescence at each temperature, and then plot the mean fluorescence as a function of a temperature. And then in that case, we observed that as the temperature decreases, the mean fluorescence is shifted to the longer wavelength region, as we see over here. Like I said, the mean fluorescence is going to help us to determine which pump wave to select for our cooling, the cooling of our material. And the absorption spectra was also determined. Based on our measurement, we use our fluorescence spectra to model the absorption spectra by using the reciprocity method, which we determine the absorption cross-section of the fluorescence spectra. This is a partition function of the excited state, and then the partition function of the lower state, because each of the state, which is the ground state and excited state, have a different level. They have different stack energy level within each state. So you use the persisting function to model for this. And this is the pump wavelength. This is the energy between the lowest level of the ground state and then the lowest level of the excited state. And then this is the corresponding temperature. This is a Boltzmann constant, which is a constant. And then if I know my absorption coefficient, then I can calculate if I know my absorption cross-section, I can calculate my absorption coefficient by knowing the concentration of the ions in my material. So based on that, we compared the absorption coefficient measured with that of the modeling from this one. And for the room temperature in all the three crystals, we observed strong correlation between all of them. But as the temperature decreases, we observe sharp drop in the measured absorption coefficient. And even the signal to noise ratio becomes very high. But like I said, what we have to know that the accurate value of the absorption coefficients is required for modeling the cooling efficiency. That was the reason why we did the model to compare with the measured absorption coefficients in all cases. Similar observations were also observed from the thulium KPB and then the YAC also. The reason why we see a lot of signal to noise ratio in our measurement may be due to the ray absorption from the impurities in our material. I cannot say that our purification process was that perfect. Well, let's move on to the last part, which is the laser cooling part. So the laser cooling part, what happens is that because I know my pump wavelength, I know my mean fluorescence wavelength at room temperature, and that was 1.82 micron. So I believe that if I select any pump wavelength above 1.8 micron region, I should expect to see my material cooling down. So we selected 1907 thulium fiber laser. And then what we did is that we mount our crystal on a glass or a very thin fiberglass. And then alongside, we mounted an undoped corresponding KBC or KBC on it as a reference sample. We irradiate the crystal for about 25 minutes for it to attain equilibrium temperature. And then we use an infrared camera to record, to take an image And then after that, we use another techniques called fluorescence intensity ratio by using erbium KPC. The reason why we use the erbium KPC is that it has already been used by most people for temperature sensing. Because there is what we call the two thermocoupling excited state. And this produces temperature-dependent emissions. As you increase the temperature, one of the emission peaks decreases correspondingly. So we use that one for a calibration. So what we did was that we mounted a small piece on the side of our crystal, and then we radiated that one with 976 diode laser. We collect the emission from 500 to 600 micron region. And then after that, we turn this diode laser off. Excite the crystal with the thulium fiber laser for about 25 minutes with an average power of 3 watts. And then after that, when it reaches equilibrium, we then excite the erbium KBC with 976 diode laser, and then collect the same emissions at 500 micron region to 600, at 500 nanometers to 600 nanometers. After that, what we did was that we did temperature calibration, sensing calibration for the erbium KBC. And what we observed is that as we increase the temperature, these emission peaks that we see around this transition decreases, and this one increases up. So we normalize this one up and then use fluorescence intensity ratio techniques to calculate for C and then calculate for the energy gap between these two transitions. And then we obtain this calibration curve from 550 Kelvin to 300, and then from 300 to 380 Kelvin. So based on this, we then plug in our intensity ratio for our main crystal into this equation, and then obtains the corresponding temperature of each of the crystals that are dealt with. Hence, we started with this is the results. We started compare the image with the fluorescent thermometry techniques. Here, for the erbium KBC, this is the reference sample. We realized that the thulium IR exhibited some clear heating over here. When compared with the reference sample, the temperature difference was 0.9 plus or minus 1 degrees Celsius. And then we use the fluorescent thermometric techniques. And we realize that if you normalize it, the increased intensity, the black one that you see here, is before we irradiated our main crystal. So that is our reference temperature. And then this is after irradiation of the crystal for about 25 minutes. And then we saw that the difference in intensity ratios are very small. Henceforth, we plug this intensity ratio into our calibration equation, and then the same thing for after the irradiation, and then determine the temperature difference between these two. Based on that, we observe a temperature difference of 1.6 plus or minus 5, which almost is closer to this one that we see over here, with uncertainty of 0.5 degrees Celsius. And then we repeated the same procedure for the thulium KPC. This is a reference sample. This is the actual crystal. And in this case, it was very difficult to actually just look at the infrared camera and determine clear differences between these two. So there is a software available that will allow you to take a region of interest of your crystal that is actually going to give you the actual temperature of the crystal. So that software was used specifically for infrared camera imaging. So in that case, we compared with the fluorescence techniques. And naturally, you don't really see any much difference in before and after. Before and after hitting the crystal. In that case, we observe a temperature difference of, for the infrared camera, 0.3 plus or minus 1, and that of the fluorescence techniques, this, which is almost closer. But what we have to see that none of these crystals show any cooling. We didn't see any net cooling. But the good thing is that what we find it very fascinating is that this is within the threshold level of cooling down. So as we go on, I will explain why. Similar thing was also observed in the thulium KPB. And then the temperature difference were as close as the thulium PC. In this case, no cooling was observed. So we did a little bit of modeling of the cooling efficiency, where we first started with the ideal cooling efficiency, which gives us the upper limit for possible cooling performance. In that case, we assume that there's no background absorption. And then we consider quantum efficiency of 100% by using this formula here. And in that case, we expect to see that the cooling efficiency for optical refrigeration should be positive, and then the negative side should be the heating side. So based on that, we compare with the absorption cross-section. Here, this is the ideal cooling line, which is a red line because we have 100% quantum efficiency. But then we decided that why don't we look at the effect of the quantum efficiency on our crystal? And then in that case, we actually reduces the quantum efficiency to 98%, 95%. And then we observe that the crossover between the heating and cooling as the quantum efficiency is decreased, is shifted to the longer wavelength region here. As you see, as the external quantum efficiency goes down, the crossover is shifted to the longer wavelength region, who tells us that if the quantum efficiency decreases, we expect to see heating of our crystal. And then we also decided to model for the background absorption coefficient. In that case, we considered 3 background absorption coefficients from a reference pipette. And that one, we also observed that based on that, we were able to calculate absorption coefficient based on one absorption spectra. And with that one, we plug in our value, and then we observe that as the background efficiency, background absorption decreases, the cooling efficiency that we see here also increases. This is 0.2, and then the dotted black line that you see here is 0.4, and then this is 0.6. Sorry. So what we observe is that as the background absorption decreases, we see a very sharp drop in the cooling efficiency. And this might be due to the decrease in absorption coefficients at the long tail region. Well, we were wondering why we didn't see cooling. There might be some issues why the material didn't cool down. And we believe that it could be due to, one, multiphenom realization. Hence, we run a temperature-dependent lifetime measurement on each of our crystals. And then we observe that as the temperature increases, the lifetime of the crystal also decreases. And then what we believe that this might be due to, one, fluorescent quenching due to energy transfer between the thulium ion and then other impurities present in the crystal. And also, like I said, non-radiative decay must also be an issue. That is why we did not see any cooling, because the non-radiative decay can degrade the external quantum efficiency, which decreases the cooling efficiency and therefore lead to heating of the material. Finally, we use the quantum efficiency model to compare the total lifetime, and then in that case we observe that here the non-radiative decay due to multiphenol realization has no effect for the thulium KBC and KPB on the total radiative decay. Henceforth, if we apply this one to determine the quantum efficiency, we expect to see 100% quantum efficiency from these two crystals. But in this case, the non-radiative radiative decay due to multiphenol realization at 300 Kelvin and 77 Kelvin also have some contribution to the total radiative decay. And that is why, if you remember when I show you the cooling, the thulium here actually show clear heating compared with the reference sample. Finally, we decided to investigate contribution from OH impurities. And then behold, we find presence of OH impurities present in all our crystals. And that one also can contribute to energy transfer from the thulium or the crystals to the OH, which is going to decrease the quantum efficiency and then causing heating to our crystal. And we also found out that other transition metals, impurities such as carbon, cobalt, and then iron, can also be found present around 2 micron region, as we see over here. This is a 2 micron region, and this is where they occur. They have high absorption cross-section area within this region. And this can also affect our crystal, henceforth can prevent it from cooling down to specific temperature. So to improve on this, all these issues that we have to be taken care of before we can actually see our material cooling down, which we're currently working on that. Okay, well, in my conclusion, I've shown you the absorption and fluorescent properties of the thulium doped crystals. And we did an evaluation to analyze application for cooling around 2 micron region. We also determined the heat load on our crystal by using 1.907 micron thulium fiber laser. We use a single pass. Some people are trying also to use what they call multiple pass, where they put high reflecting lenses on the opposite side so that the beam can bounce back and forth and then spread quick throughout the sample, henceforth can actually cool down the material very efficiently. And then what we observe is that we believe that these materials can actually cool down to temperature of around 150, which we currently work on. So what we have observed is that the impurities in this material might be the main issue. So what we doing right now is that the actual crystal is being grown by a company in Canada, where they are going to actually do the real purification process for us. And then probably we will try it again and see how it's worked, because we expected that it has to cool down to a certain temperature. Based on this, the main factors that we are worrying about right now is the OH impurities and then the transition metals. Thank you.